In this work, we introduce ALGAMES, an augmented Lagrangian game-theoretic solver. Traditional approaches to multi-agent planning adopt a predict-then-plan architecture. First, predictions of other agents' trajectories are computed. Then they are fed into a planner that considers them as immutable obstacles. This approach is limiting, because the effect of the robot's trajectory on the other agents is ignored. In addition, it can lead to the frozen robot problem that arises when the planner finds that all paths to the goal are unsafe. It is therefore crucial for a robot to simultaneously predict the trajectories of other vehicles on the road while planning its own trajectory, in order to capture the reactive nature of all the agents in the scene. ALGAMES provides such a joint trajectory predictor and planner by considering all agents as players in a Nash-style dynamic game. We envision ALGAMES being run online by a robot in a receding horizon loop. At each iteration, the robot would plan a trajectory by explicitly accounting for the reactive nature of all agents and its vicinity. This work focuses on finding Nash equilibrium solutions to dynamic games, as this type of solution is not assuming any hierarchy between the agents, and tends to generate behavior where agents share responsibility for avoiding collisions. On the contrary, Stackelberg equilibrium solutions often lead to overly aggressive behavior for the leader of the game. Our solver is aimed at finding Nash equilibrium for multiplayer dynamic games, and can handle general nonlinear state and input constraints. Handling constraint is particularly important for robotic applications, where the agents often interact through their desire to avoid collisions with one another or with the environment. Such interactions are most naturally represented as state constraints. In dynamic games, all agents interact through a joint dynamical system. They influence a joint state X through their individual control inputs U. For clarity, we only present the two-agent case. Agent 1 tries to minimize its cost, J1, by choosing an appropriate sequence of controls, U1. For instance, this cost function could encode a desired speed or a desired lane in the autonomous driving context. The agent also has to respect constraints, like collision avoidance. The same is true for agent 2. To translate the fact that each agent acts optimally at a Nash equilibrium, we derive the augmented Lagrangian associated with each optimal control problem. Then we leverage the fact that, at an optimal point, the gradient of the augmented Lagrangian is null for all the agents. This provides us with a set of equality constraints that forms a root-finding problem, which we solve using a Gauss-Newton method. We apply ALGAMES in the autonomous driving context. Indeed, many maneuvers like lane changing, ramp merging, and intersection crossing involve a high level of interaction between vehicles. We assume a single car is computing the trajectories for all cars in its neighborhood, so as to find its own trajectory to act safely among the group. We use unicycle dynamics and we enforce collision avoidance constraints. We construct individual cost functions by summing a quadratic cost on the state and control variables to a non-convex cost on being too close to other vehicles. We compare ALGAMES to a state-of-the-art dynamic game solver through a Monte Carlo analysis. We find that our algorithm solves dynamic games 3 times faster than the baseline on average. In addition to this, in 99.5% of the cases, ALGAMES is able to find a Nash equilibrium solution that satisfies the constraints. This illustrates the reliability of our approach on autonomous driving problems. We implement a model predictive controller, which executes ALGAMES in a receding horizon loop. For a 3-agent scenario, our controller reaches an update frequency higher than 60 Hz. We compare this model predictive control implementation of ALGAMES to a non-game theoretic baseline on a crowded ramp merging, which is known to be conducive to the frozen robot problem. The baseline, which follows the predict-then-plan approach, fails to find a collision-free merging maneuver. Therefore, the only option left for the merging vehicle is to wait for the other vehicles to pass before merging. Through a Monte Carlo analysis, we show that this issue, called the frozen robot problem, occurs in 85% of the cases for the non-game theoretic approach. On the other hand, our method generates merging trajectories that avoid this issue in 96% of the cases. The results we obtain from ALGAMES are promising, as they seem to let the vehicle share the responsibility for avoiding collisions, leading to natural-looking trajectories where agents are able to negotiate complex traffic scenarios that are challenging for traditional trajectory planners. We have made our implementation of ALGAMES available on GitHub. Finally, I want to thank my co-authors and advisors at Stanford, and thank you for watching.